Extrema of functions of two variables. We extend the topic of extrema from Calculus 1 to talk about extrema, that is relative or absolute minimums or maximums on a function. But here the function z can depend on x and y, or could depend on three variables for that matter, but we limit our talk to a function of two variables. The extreme value theorem, interestingly, was proven by Karl Weierstrass, German mathematician who has given to calculus the rigor by which today we prove using epsilon and delta in a very systematic way of trying to come to a conclusion of a particular mathematical matter. The extreme value theorem says that if a function f is continuous, here two variables that could be extended, by the way, defined on some closed, that's the key, closed bounded region R in the xy plane, then there is at least one point in the region R at which f achieves, according to the original um, theorem, that f achieves, it says, an extrema. And now we have translated that to mean in two cases that f, if the function is continuous in some closed interval, it has a minimum and then also a maximum, at least one maximum value. We define the relative extrema for a function of two variables, that f is defined a function in some region R containing some point x naught, y naught. Then we say that the point x naught, y naught is a relative extrema if that point is less than or equal to all the function values within that particular region. Here that region is defined as the open disk. So here R um, is said to contain an open disk. Just a ball or a sphere, if you will, with some radius delta. Secondly, the function f has a relative maximum at the point x naught, y naught if all function values are less than or equal to f of x naught, y naught in some open disk containing x naught, y naught. Now, this brings us to just a very interesting concept, and we use this to be able to get the extrema, the same idea for calculus 1. We apply it here for calculus 3, and that is the question of the critical point. Same definition, let f be defined on some here open region or containing x naught, y naught. The point x naught, y naught is said to be a critical point if two things happens. Well, here one of two things, I should say. The two things that I'm referring to first is that the partial derivative of f with respect to x at that point must be equal to 0, and the partial derivative of f with respect to y at that point is equal to 0. Or the second thing, that the partial derivatives at that point does not even exist. So either way, we call x naught, y naught a critical point. To be able to get the extrema, that is the relative extrema, we use the second partials test. The second partial test will be able to give us whether or not a function has a local minimum or local maximum. Sometimes there are functions by which there is neither a relative minimum nor a relative maximum. Thus, the function is said to have a saddle point. And you can look at this hyperbolic paraboloid, and obviously right there where you sit on the saddle, you see that here you have a minimum, but also if you follow the trace, you have a maximum. So you have, if there's both happening at one point, a minimum and a maximum, which seems like a contradiction, we call that point a saddle point. Second partials test says that first you want to find the critical values at the point AB. So you set the partials, the first partials equal to 0, and then you solve for x and y. That should give you some value here, a comma b. Then you find the all of the second partial derivatives. There are 4 of those, and you construct the determinant of the 2 by 2, which consists of the second partial derivatives. If that determinant 1 is positive, and if the second partial of f with respect to x is positive, and it could also be the second partial of f with respect to y. That could be positive. If that's positive, if d is positive, then it is said here to have a relative minimum. If the second partial is positive, that means that the concavity is upward, and so you have a minimum. The second statement, if the determinant is positive, and if the second partial with respect to x is negative, right? That means that the concavity is going down. So then you have a relative maximum, right? The maximum there. If the concavity, second derivative from calculus 1, second derivative is positive, then you have concavity that is, if the second derivative is positive, is here negative. The second derivative is negative, then that is said to have, if the second derivative is negative, then the concavity, yes, is going down, so you have a maximum. If the second partial derivative is positive, the concavity is up, so you have a minimum. Okay, got it. And then part 3, if the determinant is less than 0, then automatically you have a saddle point, as in the example that was up above. If d is equal to 0, then you cannot use this test. Let's look at a few problems here. So we first start by finding the critical point. So we find the partial of h with respect to x. We have 80 minus 2x. And if we set this partial equal to 0, that implies that we have 80 minus 2x equal to 0. That implies that x is equal to 40. Now the partial of h with respect to y. Here we get 80 minus 2y. We set this partial equal to 0. So we have 80 minus 2y equal to 0. That implies that y is equal to 40. Now we find the second partials. Look at the partial of h with respect to x, and then we take that derivative again with respect to x. It gives us negative 2. We found the mixed partials. The mixed partials, you recall, the second mixed partials are the same. So we have here the partial of h with respect to x. Now you take the partial of this guy with respect to y, you get 0. Again, the second partials are the same. And then we find the partial derivative of h with respect to y again. So we look at this guy, find the partial of this partial derivative with respect to y, that gives us negative 2. Well, from here, we can build our determinant. Negative 2, 0, 0, negative 2. This gives us 4. 4 minus 0 is 4. You just want the sign is positive. And the second partial of h with respect to x is negative 2. Is less than 0. So here that says that the concavity is going downward, so you have a relative maximum. Relative maximum at the point x is 40, y is 40, and then h, when you plug in h at 40, comma 40, you get 80 times 40 plus 80 times 40 minus 40 squared minus 40 squared. Somewhere I did that. We get 3,200. The next problem, we find the critical point. Now, if you set this equal to 0, so this implies that negative 6x plus 3 is equal to 0. That implies that x is equal to 1/2. Find the partial of f with respect to y. So we get negative 4y minus 4. If we set this partial derivative equal to 0, then here we get negative 4y minus 4 equal to 0. That implies that y is equal to negative 1. So we find the second partials. Find this derivative with respect to x again. That gives us negative 6. Find the partial of this derivative with respect to y. We get 0. The mixed partials are 0. And then the partial of f with respect to y twice. That's negative 4. So the determinant, negative 6, 0, 0, negative 4, gives us positive 24. It's positive. And the second partial of f with respect to x is negative. So again, if the concavity is negative, we have a relative maximum, right? Relative maximum. At the point 1/2, comma, negative 1, comma, and work that one out as well. 31/4. Let's look at this next one. We find the critical value. Find the partial of z with respect to x. We have negative 10x plus 4y plus 16. The partial of z with respect to y is 4x minus 2y. Now we set these partials equal to 0. And this implies here that we get negative 10x plus 4y is equal to negative 16. And the partial of z with respect to y equal to 0. That implies that 4x minus 2y is equal to 0. Now we simplify this and take that first equation. I'm going to divide it by a 2. So I have negative 5x plus 2y is equal to negative 8. This is 4x minus 2y is equal to 0. And I divided the first equation by a 2 to get similar terms here, so I can cancel out the y, add the corresponding parts, and we get negative x is equal to negative 8. X is equal to 8. So if x is equal to 8, we solve for y. Notice from this equation here, this is 4x minus 2y is equal to 0. That implies that 2x is equal to y. So if that be the case, if x is 8, then y is equal to 16. So 8, 16 would serve as our critical point. And we find the second partials. Partial of z with respect to x twice gives us a negative 10. Partial of z with respect to x and then y, that's equal to 4. The mixed partials are the same. Partial of z with respect to y twice is negative 2. So the determinant, negative 10, 4, 4, negative 2. So we get 20 minus 16, that's 4. It's positive. In the second partial of z with respect to x is negative 10. So the concavity is negative, so we have a relative maximum. At x equal to 8, y is equal to 16, and then the z value is equal to 74. All right, let's look at number 15. We find the partial of f with respect to x. So this is 1/2 times x squared plus y squared to the negative 1/2 times 2x. So that gives us x all over the square root of x squared plus y squared. And the partial of f with respect to y is similar. This is y divided by the square root of x squared plus y squared. Now, if we set this partial derivative equal to 0, and if we set this partial derivative equal to 0, this implies that x is equal to 0, and this implies that y is equal to 0. If you take this part and multiply it by the denominator of the square root, you get x equal to 0. Take this equation and multiply it by the denominator, you get y equal to 0. So you have x equals 0, y equals 0. Now I caution you not to even consider finding the second partial derivatives because it's going to be a whole lot of work. But look at this function. This function is always positive for any choice of x and y. This function is always positive, and if it's always positive, then the most minimum value that you have will be at the origin, x equals 0, y equals 0. So here we say, since f is always positive for all x, y, then f has a relative minimum at 0, 0, plug in x equals 0, y equals 0, even I know that, f is equal to 0. Well, unfortunately, I'll stop right there.